Okay, it's from University of South Carolina, Yuankai Teng. Yuankai, can you share on the screen? Okay, good. So the talk title is Learning Green's Functions of Linear Reaction-Diffusion Equations with Application to Faster Numerical Solver. So Yuankai, you can start.
Okay, so hello everyone. My name is Yuankai Teng, and I come from Department of Mathematics, University of South Carolina. Today, I would like to share my recent work, learning Green's functions of linear reaction diffusion equations with application to fast numerical solver. This work is collaborated with Xiaoping Zhang from Wuhan University, Zhu Wang and Lili Zhu from University of South Carolina. Here's the outline of my today's talk. The first part, I would like to introduce the background and motivation. The second part is going to introduce my proposed work, GFNet. And then I will introduce some experimental results, and last one is the future work. So here I would like to introduce some basic information about the fully connected neural network, which is used in my work. So the feature and information extraction inside each layer of a fully connected neural network can be considered as a composition of an affine transformation with a nonlinear activation function. You can see in the graph below that you can take n-dimensional input, and then you will get several or different dimensional output. So here I put output dimension as 2 and input dimension is n. Then you can contact it as a activation function sigma with the affine transformation. And typically we can use tiny edge sigmoid or ReLU as the activation function sigma. And then as for the multiple layers case, deep neural networks is constructed by the multiple interconnected layers. It is typically we can rewrite it as the d different layers composited with different activation functions, and then we can concatenate that to input. And a network with 4 hidden layers with depth 4 is shown below. And now I would like to introduce some basic problem formulation. So here in this work, we consider the linear reaction diffusion operator defined on the domain omega in RD, and then where the A is the diffusion coefficient and Rx is the reaction coefficient. The corresponding linear reaction diffusion problem with a Dirichlet boundary condition usually is as LUX equals to F, and UX equals to G on the boundary, where F here is the given source term and G is the Dirichlet boundary condition, which is also given. And then we can know that if we can know the Green's function, which represents the impulse response of this PDE subject to homogeneous Dirichlet boundary condition, we can solve this problem with the numerical integration with different source or the boundary conditions in equation 4. And here we should know that the Green's function defined in the omega is symmetric. And also that since that Green's function on the general domains usually do not have analytical formulas, typically we do not use this kind of method to solve the problems. So here we propose our method GFNet to first approximate the Green's function on arbitrary domain, and then we want to solve the linear reaction diffusion problems with various source terms and Dirichlet boundary conditions without the need of retraining. So here I would like to introduce some related work. So first, our method is based on Teng, the physics-informed neural network, which represents a mapping from spatial or temporal variables to state of the system by different neural networks. And it is then trained by minimizing the mean squares of the residuals of target PDEs at randomly selected interior points, typically sampled by LHS, and the errors at initial or boundary points. So in this case, if we want to solve the linear reaction diffusion equations defined in equation 2, we can first construct a d-dimensional input and one-dimensional output. And after the training process, this network can be considered as the approximation of the U. In order to train this network, we need to sample points. The point-wise defined residual of the equation 2, including the constraint on the boundary, will be minimized to optimize the parameters in the network. And here in the loss function, the first part is the residual of PDE, and the second part is the constraint on the boundary. Here we need to sample points in both inside the domain and on the boundaries. Other than the pin, we also have some other network method to solve the PDEs. The first one is the deep-read method, which considers the variational form of PDEs. It combines the mini-batch stochastic gradient descent algorithms with numerical integration to optimize the network. And the second one is DeepNet, which is introduced by Lulu. This method extends the numerical approximation theory for operators to neural networks, and it contains two subnetworks to encode the input functions and its transform location variables respectively. And then it has very powerful generalization ability to handle diverse linear explicit and implicit operators. And last one is more related to our work, the deep green. It will it aims to solve the nonlinear problems. So it will first linearize the nonlinear problems using a dual autoencoder architecture, and then it will evaluate the Green's function of the linear operator and inversely transforms the linear solution to solve the nonlinear problem. So next, I would like to introduce our work. So since we follow the basic structure of PIN, so we still use the fully connected neural networks here, but we add some modifications. So you can see from the first two lines, which the first line is the input of our method. Here we take a two-dimensional problem as example. So we consider X and C as the input, and then this X C will fed by an auxiliary layer without any bias and activations to transform it to X C and X minus C, since that we consider that X minus C is also kind of representation of Green's function. And by this, we hope that our method can kind of speed up the training process. And then in order to train the GFNet, we approximate the direct data function by a Gaussian density function. Here, the 2D case is shown here, where S denotes the standard duration of the distribution. As S tends to be 0, this function approaches to the direct data function. But also, by this kind of approximation, the truncations will occur when the KC is close to the boundary. Here, we show the example of this approximation on a square domain. It is -1 to 1 square, and we choose the source point at -0.7 and -0.096, which is 3s away from the boundary. And you can see from the left to right, if S is smaller, the zero boundary condition of the Gaussian density approximation will be satisfied. However, in real experiments, we cannot use this smaller S due to the difficulty of training process. So in order to train the network, we have to apply the locally defined X sampling strategy for a given Z, since that the different distribution of Gaussian density function is different with different given KC. So if we are suppose that we are given 3 data sets of X generated by a match generator or any other efficient sampling method like Monte Carlo or LHS from a high resolution to low resolution. We name them as VX1, VX2, and VX3. We collect the X samples based on the following strategy. So first, we will evaluate the distance between X and a given KC. If it is smaller than C1S, we will choose the samples from the high resolution mesh. And if it is greater than C2S, we will collect the samples from the lowest resolution mesh. And if the distance is greater than C1S and lower and smaller than C2S, we'll choose the samples from the middle resolution. So in the graph below, you will see that when we give the example of our chosen examples for different domains with different KC. The first one is the square domain. It is -1 to 1 square. The second one is annular domain. It is a circle with radius 1 without a circle with radius 1/2. And the last one is L shape. It is -1 to -1 to 1 square minus 0, 1, 0, 1, 0, 1 square. So after finding the choosing the sampling strategy for X, we would like to find the efficient sampling strategy for X for Kasi to form our final training data. Ideally, that we hope that we can train one network to represent the whole behavior of Green's function on the given domain, but we cannot do that since the large amount of training data cannot be handled by the limited computational budget. And the second one is that the Green's functions corresponding to different Kasi behave significantly different, but it can be solved individually. Therefore, we propose a domain decomposition strategy to train a set of Green's functions, GFNets, instead of training the global one. And we still take the two-dimensional case here as the example. We will first divide its circumscribed rectangle into n by n different blocks uniformly. And then suppose there are k blocks containing the samples of Kasi, and then we will choose the Kasi in different blocks, and then we generate X samples for each Kasi in each block, and last we define the sample set for the case Kasi block as the total samples together. So after we have generated the samples for training the case GFNet, we will train the GFNet with the following loss functions. The first part is the point-wise defined PD residual, which is similar to the pin. And the second one is the constraint on the boundary. And the last one that we hope our network can keep the intrinsic symmetric property of Green's function. So we hope that we enforces the network to obey the symmetric property. And we put it as the last part of our loss function. And here SC is the interior training samples, and SB is the training samples on the boundary. And then I would like to introduce the fast numerical PD solver using our GFNets. So recall that the solution of linear reaction diffusion problem in equation 2, it can be solved based on the formula 4, which is the integral part of that. So here, if we can get the Green's function G with different source term F and different G, different boundary condition G, we can evaluate the different solution U by numerical conjectures on the triangular meshes. So here we show our integration method or the conjecture method at below. That from the graph, the green interior points is the X we choose here, and the blue dots is the conjecture points in triangular elements. We here use the 4 points in conjecture rule for Kasi, and on a boundary that we choose 3 points for Gaussian conjecture rule. And here, and then we like to introduce some experimental results of our work. So before that, I would like to introduce the consider domains and the numerical evaluation method. So first, we will consider both the Poisson's equations and a reaction-diffusion equation in our work on 3 different domains. The first one is square domain, -1 to 1 square, and the second one is annular domain. It is a circle in circle with different radius, and the last one is L-shaped domain. And the numerical solutions of our PDEs at all interior vertices will be used for quantifying the performance. And the relative L2 norm is defined here, where the AX is the area of the dual cell relative to the vertex X, and the UE and the UP denote the exact solution and approximate solution respectively. So here we like to introduce some ablation study. So the first part is that the ablation study on Green's function with a fixed point source. We choose the classic Poisson equation in a unit disk with a fixed point source located as the center as the example to conduct the effect of the learning accuracy and the effect of using the symmetric loss term LC. The analytic form of this specific function is given as below. That since only the origin is the Kasi, so we only need to sample X once. So 3 different levels of meshes is given here, and no domain partition is used since there's only one source point. So here is the here's the result of our learned Green's function. So since that the singularity will occur when X is when it's close to the Kasi, so we calculated the relative L2 arrow in bore with a small center removed, where you can see here the sigma the epsilon equals to 3s to avoid the singularity at origin. So quantitatively, that we find the relative L2 arrow is about 1.29 multiplied with 10 to -3. So the arrow mainly concentrated on the center, and it will decay rapidly to the boundary. And next part that we want to test the effect of symmetric loss to the learning outcome. So we train the model in 2 ways. The first one is that we include the symmetric loss, and the second one is that we exclude the symmetric loss. So from the result, you can see the left graph is the symmetric of the Green's function. Is the Green's function with symmetric input, and the second graph is that our approximated result with symmetric loss, and last one is our approximated result without the symmetric loss. So we see that adding the symmetric loss, it is the accuracy is apparently improved of our predicted Green's function. And then we want to do some ablation study based on the Poisson's equation on omega-1. Here we would like to investigate the effect of the domain partitioning strategy and the choice of Gaussian parameter S. So we consider the Poisson equation here, which is the pure diffusion case with A equals to 1 and I equals to 0. And we consider 2 different Dirichlet boundary conditions. The first one is homogeneous boundary condition, and the second one is inhomogeneous boundary condition. So for training the GFNets, we choose the parameters here. So we first will sample 545 different Kasi on the domain, and then we divide it into 4x4, which is 16 different blocks, and we choose the samples from X with C1 equals to 5 and C2 equals to 10. So first we test the impact of the domain partitioning strategy on GFNets, considering 3 different blocks, 4x4, 5x5, and 6x6. The trained GFNets will then use to solve the Poisson equation, and we evaluate the results on 3 different resolution grades. So from left to right, you can see that with greater divisions, the accuracy will improve slightly. And from top to down, you will see that even though we use finer and finer mesh, the accuracy will not increase significantly. This is because that this arrow or this accuracy is already dominated by the performance of our learned Green's functions. So this arrow is dominated by the performance of GFNets. And here is the results of the solutions of Poisson equation on omega-1 under cases 1, the top row, and the cases 2 on the bottom row. So you can see that our results is kind of acceptable. The arrow is kind of distributed symmetrically. And then we want to test the effect of Gaussian parameter S. The value of Gaussian parameter S plays the most important role in accurately approximating the direct delta function, which will further influence the performance of our learned GFNets. So here we test the numerical results of predict solutions to Poisson equation with two different S. The first one is 0.02, and the second one is 0.015. And we choose 6x6 subblocks here. We will first train the network with S equals to 0.02, and then we fine-tune our network with S equals to 0.015 based on our pre-trained network, and then we get the following result. So you can see here, with smaller S, the accuracy will slightly improve, and here you can see that the error is no longer dominated by GFNets in some case. So here it illustrates that our GFNets is more sensitive to the choice of our parameter S in approximating the Gaussian delta function. And then we would like to share some result of our learned Green's functions for Poisson's equation on 3 different domains. So here we show you the training parameters for the other 2 domains, and the bottom is our predict Green's function on the 3 different domains. And also we would like to share the results of our Poisson's equation. Here we only show the inhomogeneous boundary condition in omega 2 and omega 3. So similar to the case in omega 1, the arrow in our result is still symmetric, and the predict solution is kind of acceptable with respect to the mesh here. So here we will also to demonstrate, if we want to demonstrate the accuracy and efficiency of our proposed method as a numerical solver to the target PDE. So we also compare the numerical results of our method to the finite element, which is implemented by the Phoenix. So here we use 3 different quadrature mesh as the input mesh of Phoenix, and then we measure the numerical errors and the time we use to inference. So here you can see that our method is able to predict the Green's function. Our method is able to predict the solution accurately when comparing to the finite elements, especially on the chorus mesh that our method can build finite elements. And with the increase of mesh with mesh grid, with the size of mesh grid, that our method still have the compatible accuracy compared to the finite element method, and the time we consume to construct the result is also competitive to finite element method. So here I would like to mention that our method is purely parallelizable, which means that if we have enough training machines and GPUs, that our method can the time for training and inference can be further reduced. And next, I would like to introduce our learned Green's function for linear reaction-diffusion equations. So here we test the following reaction-diffusion operator, and the trend parameters is the same as we previously defined for the Poisson's equation. And here is the predict Green's function for this reaction-diffusion case. And we consider the exact solution chosen as below, and the Dirichlet boundary condition are correspondingly determined. And here is the arrow that we evaluated on these 3 different domains with different quadrature mesh. And here's the result of the numerical solutions for linear reaction diffusion equations. So And our future work is about, so firstly is that since that we need to approximate the delta function to put it as the right hand side to solve to learn this GFNet. So how to choose the sampling for so how to solve the problem when the source point is close to the boundary is very important to improve the accuracy and efficiency of our method. And then we can consider to use the Hard constraint to train Green's functions. Since that the zero boundary condition will be automatically satisfied, so we can ignore the first problem. And then we would like to extend our method to different boundary conditions. And the last one is that how to adaptively sample the strategies for X would be further investigated to reduce the data usage and achieve the higher accuracy for approximating the PDE solution.